Well, let's look at the recap from last week. Okay. So from last week, there were a few things that we looked at. We we pretty much went through what deflections. What we define deflections. So we defined. Oops, this is too thick. Okay. And then we mentioned that deflections do occur usually when there are loads on the structure, when there's I think temperature changes. We also have settlements in structures or in buildings, and also in fabrication errors, right? But one of the most common, especially with reinforced concrete design, has to do with the loads, right? So the loads can be the occupancy loads, or it could be the dead loads, which will be the loads from the structure itself, and some other loads we tend to stay longer with the structure. All right. And then we also looked at the fact that when there are deflections, so if you have a beam and that beam undergoes some form of deflections based on loads which are on it, so it deflects within a certain shape. Okay. And we call that shape the deflected shape. Okay. So this deflected shape can also be seen as the elastic curve. Okay. Because we are assuming that the deflections occur within the elastic region. And I explained that the elastic region is a region whereby when you apply some load to the structure, it deforms. Then when you take the load away, the structure returns to its initial position. All right. So anytime that happens within a structure, then it means that that structure is behaving, or its behavior is limited to the elastic region. Then from there, I think we formulated the what's the name? The Bernoulli Euler equation, that we came up with the fact that the moment is equal to the so it's a second order differential equation. Okay, so this is the equation for the moment. Okay, which then can be rewritten in different forms, right? Whereby the squared y, the x squared, it's simply m over ei. And then we also went through how to take this information and then use that to find slopes and then find displacement. So this is called I think it's called the elastic equation for bending. You are likely to go through this again in strength of materials, I believe. Okay, so you get the opportunity to learn this one twice, which is the Bernoulli Euler equation. Okay, it's pronounced Euler, the Euler, like this. This is how they pronounce the name Euler. So we mentioned that if we are to integrate this, pretty much integrate the elastic equation. So let's say we go through one integration. Let's say integrate once, or first integration. Then it means that we'll end up with ei squared y the x squared, which is equal to m dx. All right. And then definitely if you're integrating where you don't have limits to your integration, that means that there will be a constant. All right. So this definitely would reduce to ei dy dx. Okay. And the y dx is simply the slope. Okay. When you have if you have a system like this, so back in SHS or JHS where you had let's say the Pythagoras theorem, and then you had, let's say you found delta y and you found delta x, and then you were like the gradient. Okay, it's equal to delta y over delta x. Sorry, delta x. Okay, so this is what we did back in high school. And basically what we're doing was to find the gradient, which in this case is the same as what? Slope. Right, so it's the same principle being employed in this case. So this portion here would give us the slope. Okay. Then if you integrate again, so that's like the second integration. And so if you integrate this general equation twice, so it's like integrating maybe let me say equation 2 again. So that becomes the squared y over the x squared, and that will give us m dx plus ax plus maybe b or something there. Okay. So if you integrate this section twice, you get y. Okay. So y is equal to this entire equation here, and thus then will give us the deflection, or the vertical deflection in this case. Okay. And in some instances, instead of differentiating, instead of integrating, we can also differentiate, right? We can differentiate the Bernoulli Euler equation, so differentiate it once. And once we do that, then it means that we have EI, the cube y over the x cube. And then that will be what's the name? dm dx. That will be equal to dm dx. And dm dx is equal to F, where F is the shear force. Right. So if you integrate with respect to, if we differentiate the Bernoulli equation once, you get a shear. And then if you differentiate it twice, you get the load intensity. So that's EI, the raised to the power 4, the x4 is equal to the squared m over the x squared, we're same as the f, the x. And most likely this will be a negative value, but that's something for us to look at later. So this becomes W, where W is a load intensity. So what is of interest to us as, I mean, for this particular subtopic is the integration twice. All right, so finding the deflection. So it means that this equation here will be very important to us. And in some cases also, this equation here. So the equation to find the slope and deflections will be critical to us, because that's the goal, to find slopes, to find how much certain points on the beam would rotate, and also by how much would they deflect. So that's the idea. So the steps in solving, so with this, we have what we call the double integration method. So based on the Bernoulli equations, we have what we call the double integration method, and that would be this right here. Okay. So that's a double integration method. My pen looks so okay. Okay. All right. So these are constants that we need to find. All right, the A and B. And to find this constant, we apply what you call boundary conditions. Okay. So we apply boundary conditions. Okay. To find unknown constants. Okay. Or unknown variables in this case. Okay. So that if we find yes, so yes, for differentiation, we have to subtract one from the power. Yes, that's what we do. Yeah. Um, I haven't done any differentiation. I've just written the general equation for differentiation, right? So for me to differentiate, I need to first formulate an equation for the moment. Then from there, I can do the differentiation. We should have an example shortly, all right, to explain the concept to us. So for now, all I'm writing is just equations, okay? And this, I guess maybe this is a bit confusing. So let me explain this one on the side before I go down here. The general term is EI the squared y over the x squared. So let's say the squared y over the x squared. So let me say all of this is maybe k. All right. So mean that if I'm to differentiate k, then it becomes what? The k over the x. I'm differentiating with respect to what's the name? With respect to x. So, but I know k to be what? The squared y over the x squared. So this becomes the x into bracket the squared y over the x squared. And this is the same as the cube y over the x cube. Okay, that's just the whole idea behind differentiation. Okay, we'll look at some examples, I think, maybe in the next few minutes or so. So back to the double integration method, um, we need to apply boundary conditions to be able to find the right equation that we need. So the first thing we need to do in solving these types of questions is to formulate an equation for the moment, okay, in terms of x. So the x becomes a key variable. Okay? And this is critical to whatever we are doing, okay? So I think I'd mentioned earlier that we need to take interest in that on how to write equations in terms of x, because we'll need that information going forward to analyze our structures when finding deflections. Okay. So with the example that we did last week, where we had a beam with a UDL on it, okay, where this is W and the length of the beam is L. And I think we were to find, so if I have the spot A, B, let me make this right. At midpoint, I have C. Then at the end, I have B. And we have to find the deflection at C. All right. So we are assuming that the beam will deflect somewhat like this. I mean, I'm just exaggerating the deflection in a way. Why is this not working? Okay. So I have this deflection, this form. So I'm finding the deflection at C. Yeah, so delta C or delta C is the same as YC. Anyways, all right. So here I need to come up with some equation for the moments. All right. So I know that my VA and my VB, I can easily find VA, VB. So VA will be equal to WL over 2, and VB also be equal to WL over 2. Can I assume that you guys have an idea of how to find reactions and support, at least with respect to basic structures? Right. You can message me if my assumption is right or wrong. So with this in mind, I cut a section somewhere here so that I end up with a beam. So this is W, and then this distance here is X. All right. So basically, I want to find the moment at this point where I'm highlighting with the see the sea blue color also. Okay. So that moment at X will be equal to WL over 2. So it's force times distance. The distance is X, and this is causing what's the name? Clockwise rotation. So basically, I want to find this moment, which I don't know. Find the moment here, mx. All right. So typically, we assume that is anti-clockwise. So it take moment about mx. So with respect to the reaction is WL over 2 times x. Then you have with respect to the UDL, it becomes WX, which is the load, times half of x. All right. And this becomes your equation for your moment. Okay. So this can be simplified further to WLX over 2 minus WX squared over 2. Okay, so this is your moment equation. So now if you take the double integration equation here, all right, and then you input in, so wherever you see m, you input in your WLX over 2 minus WX squared over 2 equation to that, then you can do your integration. Okay. So we want to find the deflection, which means that we have to integrate twice. Okay. So to integrate twice, we have to first do our first integration, then we'll do our second integration. So for the first integration, all right, for the first integration, it means that we'll end up with I think I left my EI here, but it's fine. So this will be equal to integration of WLX over 2 minus WX squared over 2 dx. Okay, so this integration then will give you WLX squared over 4 minus WX cubed over 3 plus a constant A. And let me call this constant C1 so that it doesn't confuse us with the A, B, C on the structure. All right, so then that becomes our first integration. Then on the second integration, okay, so it becomes EI. I can just write a general equation here. And that will be to integrate this, the WLX squared over 4 minus WX cubed over 3 plus C1. So all of this dx. Okay. So there's always that dx on the side anyways. So if you had to integrate, let me say dx, That means that we end up with WL x cubed over 12, which is 4 times 3, minus WX4 um, over what? 4, 3. I made a mistake somewhere. If I differentiate this, yes, 6. Okay. Yeah. So this is 6. Then here's 24. So then this becomes plus C1x plus C2. The x is not squared. The x is not squared because this is the steps we went through. We went through one step. So one step we had 1 dx. Sorry. We had 1 dx over here. Okay. Then we took that information for another dx. Okay. So technically, if you have to get this 2 dx, then that should be dx squared. Oh, okay. Okay. I get you. I get you. Okay. Thank you for the correction. So this is squared. Squared. Okay. So at this point, we have all of that. So from here, so this becomes your equation. This is your equation, and you need to find the constants C1 and C2. So to find the constant C1, C2, you have to use what you call the boundary conditions, all right? And the boundary conditions are usually quite interesting to use. So with the boundary conditions, so the goal is to find our C1 and C2. So we go back to our diagram. Okay, this diagram should help us. So this is X move towards this direction, and then Y move in this direction. Okay. So at A, all right, so at A, X is 0, okay, and Y is also 0 because there's not been at every support or at supports, we don't have deflections at supports. Okay. Unless otherwise intended, but normally supports do not undergo deflections, especially no, we typically know 3: the pin support, the roller support, and then the fixed support. They don't undergo vertical deflections. Okay. So when x, so at A, when x is equal to 0, y is also what? 0. Okay. So if x is 0, y is 0, and then you place them into this equation. So you place them. So substitute. Let me call this equation maybe equation 5. All right. So substitute. Substitute. I think I've written more t's than I'm supposed to. So substitute into equation 5. You would realize that then C2 here, C2 here becomes 0. So if C2 becomes 0, then it means that your equation has further been reduced. Okay, my screen is acting up. So I'll put this back. Okay. So the equation has further been reduced to, oops, sorry, I don't need this here. So WLX cube over 12 minus WX4 over 24. Okay, plus C1X. So we still need to find this other constant C1. So to do that, we come up with another boundary condition. Okay. um, which would be at maybe B. So at B over here, at that point, your X is now equal to the length of the line. Your Y, again, at this point is 0. Okay. So with these boundary conditions, you come and state it here that at B, your X is equal to L, and then your Y is still equal to 0. So you place that, let me call this equation 6. So you sub into equation 6, okay? And if you do that, you make C1 the subject, and then you end up with C1 being equal to, I think, minus WL cube over 24. Okay. So then your final equation then becomes AI, double integral of the squared y dx squared will be equal to WLX cube over 12 minus WX 4 over 24, then minus WLX L cube X over 24, where this one here represents the C1X. Okay, so let me go over the boundary condition. Okay, so when we come to the first, so there are a few boundary conditions, right? Yeah, we can formulate as many as we want, but the goal is that you come up with boundary conditions which will make your analysis easy for you. Okay, so we start with point A. Okay, at point A, x is 0, x moves from A towards B, right? So at point A, x is 0, just like on the Cartesian plane, x is 0, y is 0. So if x is 0 and y is 0, if you substitute these values into um, equation, what's the name? Equation 5. One other thing to take note is that um, double integration of a double differential, which I think maybe I've not mentioned here, is the same as the deflection. So this one becomes EIY. Okay. So this whole thing is EIY. Okay. So we still have a Y term in there, which means that EI0, because Y is 0, will be equal to WL0 cube over 12 minus W0 4 over 24 plus C10 plus C2. Okay, I don't know what's happening. Can you hear me now? Confirm if you can hear me loud and clear, please. Okay. Um, so I'm saying that when you do the double integration, all right, of a double differential, pretty much what you get um is that you get the deflection, right? Why? So which one is lagging? Is it the sound that is lagging or is the screen that is lagging? Which one comes first? The sound comes first or the screen comes first? Okay. So let me check my sound and see. Let me close a few things maybe. Those are hampering the smooth head. Just give me a sec. Okay. So let's try it again and see if something happens. Just let me know. Yeah, so I was saying that when you double integrate what's the name? When you double integrate the Euler, the Bernoulli-Euler equation, you get the deflection. Okay, yeah. So that's something to keep in mind. And with this deflection equation, you have to find the boundary conditions. The reason why we are finding boundary conditions is because we don't have the limits to integration. If you have the limits to integration, there's no need to go through the boundary condition process per se. Mhm. So we have the case for the first boundary condition to find C2, and in the case of the second boundary condition to find um, okay, so the case of the second boundary condition to find C1. Okay, so that's the idea. So once we find these two constants, C2 and then C1, then we can formulate the equation for the deflection. All right. So let me put here, this is equal to EI y. Okay. So once you have this equation, then you can go ahead and then answer the question. Okay. So the question states that we should find the deflection at C. So this is your question, find deflection at C. Okay. Yeah. So it means that at C, your X is equal to L over 2, your Y is Y at C, which is unknown. Okay, you don't know what that Y is. So that's what we want to find, okay? So you can put in, so wherever you see, so let me call this equation, this is equation 7. So you sub into equation 7. Once you substitute into equation 7, you can find Y, your YC. So here YC will be equal to WL over 12 L over 2 cube. So wherever I find X, I put in, or wherever I see X, I put in L over 2, okay. Minus W over 24, L over 2 exponent 4, minus W L cube over 24, L over 2. So you have this interesting equation. Okay, you know what? I did that last week. All right. So that because I'm just doing a recap. Okay, I did that last week. What you can do is just go through the one we had from last week and then join the two, and then you should be fine. Okay. It's just putting in wherever you see X, you put in L. So you go back to this equation here. What in equation 6, wherever you see L, wherever you see X, you put L, and then Y is equal to 0. So this is Y here. Y is equal to 0. Then you can have this nice equation to formulate that and then find your C1. Okay, try it. It's not strange. Okay. All right, then if you do all of these computations, you end up with minus 5WL4 over, so that's EI here, and then put the EI here in the beginning. EI is over here. So that becomes 384, which means that your YC here is minus 5WL4 over 384EI. You'll find this equation. You'll see this equation first. So you'll see it in Reinforced concrete design, you see this equation, steel design, timber design, any design related course you come across. This very equation. Okay, this is the equation to find the maximum deflection of a simply supported beam which has a UDL acting on it. So minus 5 WL exponent 4384 EI. Okay, you come across it later. Okay. So I think we went through some other examples also with respect to the what's the name? With respect to, I think it was a cantilever that we went through last week. And then that same approach can be used to find the deflections. There are a few more examples which I think I have posted on the V campus for you guys to go through. I'll try to give some to the TAs also. Then maybe when you guys have your tutorials, you can also try and solve them. Okay. I think that's about it. Any questions? So let's look at something new for today. Another what's the name? Uh, another method that can be used to solve the deflections and then the slopes. The double integration method is a bit cumbersome. It requires you to write the moment equations in terms of x, all right? And that can be a bit challenging if you are not used to that process, all right? So there are other methods that are much more simple that can be used to calculate the deflections, okay? And one of such example, it's the moment area method. So this is what we call a geometric method. So this is a geometric method. Okay, what it simply means that it uses the geometry of the beam and then its bending moment to formulate equations for um, or to find slopes and then find what's the name, the deflections. Okay. So basically geometric method, which I think this provides a way or a method to find slopes and deflections. Okay. It was developed in, I think, well developed by Otto Moore. So developed by Otto. You come across this guy again, Mr. Moore. You come across him, I think, in Strength of Materials. When you start looking at the more stress equations and more strains and all of that. Well, he has an interesting idea on how to derive principal stresses and all of that when you're looking at what's the name? A stress element or an element with stresses acting on them. It was developed by Otto Moore, and I think then it was stated. So when Otto Moore developed it, it was stated, or it was brought into uh, prominence by Charles Green. Okay, in 1873. in 1873, and this was um, formulated as an easier or a more simplified approach to solving what's the name? Slopes and then deflections, right? It still requires an understanding of or it relies on let me say, it relies on um, Bernoulli, just a second, it relies on the Bernoulli uh, Euler equations. So whatever we did earlier, we'll still apply it in a much more simple way. All right. So it relies on its equation, also its assumptions. And this does not, so doesn't or does not require a full integration process. Okay, so just take note of that. Okay, with a double integration method, you actually have to go through a full integration process to be able to formulate some bit of understanding for whatever you want to do. But in the case of the moment area method, as the name implies, you are looking at area, right? Moment of area. We'll look at what that is shortly. So now let's look at um, like an ideal case and then formulate the equations of the moment area method, and then we can see how to use that to solve problems. So let's say, oh no, let me check something. I want to see how small my handwriting is today. Let's say I have a beam. Okay. So maybe a general beam with some general loading on the beam. Okay, so some general loading on the beam. So some of the loads could be there could be point loads. Now, let me just use a different color. The point loads, whatever, maybe some other UDL acting on it. All right. So all of these are just arbitrary loads acting on the structure. Okay. Now let's look at key points. Let me call this point A, this point B. They are the key points for me. Okay. Now, when you take a small element of the load, okay, and with respect to the beam, you have a small section here, the X. I think this we've already gone through, but I'm just trying to explain to us. Okay. So let's say that again, there are also some loadings at the ends, maybe M1 and then M2. Right. So this is just like a general loading situation. Okay. Depending on the load, it could be a little bit more specific. Maybe you could have only just UDLs or have only point loads or have a combinations of both, or maybe have VDLs or have loads where some supports have moment and then all of that. These are all different scenarios that we can have for the loads. Okay. But we want to, what's the name? We want to formulate some equation for the slope and then the deflections. Okay. So based off this load, we can also formulate a bending moment diagram or draw a bending moment diagram. Okay. So I think that 1 hour. Okay. We'll try to take some break, maybe some 10 minutes break or so. So again, So let's say we solved this being with its load. We've done all our analysis of it. We can draw the bending moment diagram. So let me just draw something that is arbitrary again. So I have the shape. Okay. So this is my bending moment diagram for the structure. Okay. So again, I'm looking at point A here. Oops, point A over here, and then point B. They're of interest to me. Okay. I want to find something with respect to A and B. I still have that little section that I have taken to analyze my structure. So these are my supports. So this is a bending moment diagram. Now, we recall, okay, that the theta, the slope or the change in slope is equal to the m over ai dx. Okay, so we came up with this. And then if you had to integrate both sides, we came up with the fact that, okay, then it means that the theta, which is the slope, okay, is equal to the integral of m over ai dx. So what the moment area method does, okay, is that when it wants to find slopes and deflections, it usually finds these with respect to with respect to 2 points. Okay. So what it means that for slopes, you have to find slope between 2 points. Okay. So in this case, let's say between point A and B. All right. And also we find the deflection. Okay. But this deflection usually would be what we call for this deflection, let me put in asterisks. So the deflection between, again, 2 points. Okay. So for example, if I want to know the slope between point A and B, my slope equation can then be rewritten in this form. Let me use red. Okay. So theta BA, so the slope between B and A, then will be equal to, so now we have the limits, A and B, m over ei dx. Okay. So this becomes the equation for the slope between points, all right? B and A are just arbitrary points. They can be any points on the system, all right? And here, basically, it's the change in slope, okay, or the slope, which is the change in slope between points A and B, sorry, between point A and B, okay? So let me explain, and then we'll see that this actually would end up being one of the first theorems. There are two theorems that we have to deal with when it comes to the moment area method. So let me draw, let me use a ruler to draw some few things here. Okay, hopefully I can get my curve looking. Oh, cool. Okay, this is the best curve I've ever drawn. So that's supposed to be the elastic curve. Okay, so this here is elastic curve. Okay. So anytime your structure undergoes some form of bending, you are pretty much have to draw the elastic curve or the deflected shape. Okay. So here I have points A, I also have points B. Okay. So now on the elastic curve, these are the points A and B. Okay, A and B. Okay, so let's say here was the initial position of the beam. Then when it undergoes some deflection, this becomes the current position of the beam. So the current position of the beam is pretty much akin to the deflected shape. Okay. So now it means that we want to find the slope at A and B on the current position or on the deflected shape. Okay. So to do that, when anytime we are finding slope, you pretty much trying to draw a tangent to a point. Okay. That's what we have been doing all this while when we're looking at slopes with respect to what's the name? Um, Gradient and then all of that. Okay. Usually if you have your X and Y, and then you maybe you have a curve, okay. And then if you want to find the tangent to the curve or the slope of that curve, pretty much you draw a tangent at that point, which will touch the point of interest to you. Then based on that, you find your delta Y and find your delta X and then find the gradient of that particular curve. Okay. If it's a line, then it's easier because then it's just a gradient of the line which will pass through the tangent. But if it's a curve, then it's just one point on that curve. So here I have my tangent. Let me call this tangent A. Then I can also draw another tangent here, passing through B. Let me use a different color. The color will suffice. Okay, this should work. So here I have a tangent here. Okay, so this is tangent B, or the tangent passing through point B. Okay, so this is the intersection point. So this is the intersection intersection, okay, points for A and B. All right. So this angle that they make with respect to the two tangents here, this angle theta, oops, okay. So this angle, let me make the curve bigger. So this angle theta is the change in slope or the change in angle between theta B and theta A. All right, so this is how we write it. Now, when we come to B, when we come to point B, if I want to find the angle point B mixed with the horizontal, I can just draw a horizontal line at this point. Okay, so that this angle here will be theta B. The angle, what's the name? The point at B mixed with the horizontal. In the same way, when I come here to, I can draw a horizontal line, and then the angle, the tangent at A mixed with the horizontal is called theta A. Okay. So these are the key things to note with respect to finding angles. All right. So theta A, theta B are the angles the respective points make with, or the tangent of those respective points make with the horizontal. Whilst theta BA is the change in the angle between B and A. So in some instances, you can also make this analysis that, okay, the change in slope between A and B, right? So change in slope between A and B. So if there's a slope of B and this is the slope of A, then the change or the difference between the two of them should then give you theta BA. And from here, we can formulate the first theorem. Okay. So theorem number one, and it says that the change, so you're just trying to repeat whatever I've gone through. Change the slope between 2 points on the elastic curve. Equals the area of the M over AI diagram between these 2 points. So this is the first theorem for finding slopes. Okay. And this again comes back to so that if my 2 points are B and A, then theta BA, the change in slope between B and A is equal to the area of the M over AI diagram. Okay. Integration is finding area under a curve, right? Typically, that's what integration is all about. So that if you have this right here, when you integrate the M over EI diagram, it's just trying to find the area of that curve. All right. So let's see what this means in terms of solving an example. Let's say I have a cantilever. Yeah. Then has a load at the end, P. The length of the cantilever is L. These are key points. A, C is in the middle, and then B is at the end. All right. So here we are to find theta BA. Okay. And then find theta, let's say CA. Okay. So in this scenario, one of the first things we need to do is to draw the elastic curve. Okay. One of the most important things to do. Oh, okay. So so the first thing we need to do, draw the deflected shape or the elastic curve. Okay, so that's what we need to do. If you have a cantilever like this, okay, and you're applying a load at P at the end of the cantilever, then it means that it's going to deflect in this form. Okay. Last week we learned a few things with respect to the fixed support. That at the fixed support, if I call this fixed support A, at that fixed support, the rotation at that point is 0, and the deflection at that point is also 0. Okay. Which means that a fixed support will not undergo any rotations. All right, so that's how come my curve has this bit of straight line towards the supports. All right, just so that it just shows that there's no rotation at that point. Okay, let's take a note of that. So these are some of the boundary conditions to have in mind. If it's a pin support, again, let's say pin support A. Oops, I'm creating a mess. It means that theta A will not be equal to 0, but then delta A will be equal to 0 because there will be rotation at a pin support. Okay. So usually the curve for a pin support goes this way. Okay. So that you can easily draw a tangent at A. Oops, a tangent at A, and then be able to get your theta A. Whilst in the case of the fixed supports, this is how your tangent looks like. Okay. So that if you draw the tangent at A, the tangent at A would end up being a straight line or a horizontal line. All right. So let me call this tan A, tangent at A, and this is also tan A. But because of the difference was the name, the different support conditions, the fixed support would have what's the name? Would have or would have no rotations, whilst the roller support or the pin support will have rotations. So that's just to explain the elastic curve. And once we draw the elastic curve, the next thing would be to draw the respective tangents. Okay. Let me do this so that I can have a bit more space. Okay, great. So here, this is my this is my A, this is my C, this is my B. So let me draw the tangent at A. So the tangent at A will be a straight line. All right. So the tangent at A, let me use the green color for that. It's going to be a straight line. Let me just exaggerate that a little bit beyond the structure. So this is your tangent at A. And then the tangent at B, so now at B, we can also have its tangent. So now this is the new location of B because of the beam has now undergone deflection. So at B, this becomes my tangent at B. Okay, let me go with this color. Okay. So I have this as my tangent passing through B. So this is tan B, or tangent passing through point B. Okay, so the intersection of A and B is right here at this point. So this is the intersection. Okay, which means that this angle, this angle here is the angle I'm looking for. So this will give me my theta B. Okay, so that's the general idea. And then if I want to find theta B, okay, so theta B, let me just draw a straight line over here too. Oops, it's not a straight line. Okay. So this angle here is theta B. Now, let me take the information that I have earlier and bring everything out so we can see some bit of trigonometry occurring. So here I have this, and then somewhere here to have that. Okay. So this is my theta BA, and this is my theta B. Okay. So I think this should be what is it? Corresponding angles. Yeah. So using the principle of I think corresponding angles. Yeah. Which we learned in high school. So that's I think the F shape kind of. So with that, it means that theta B A is the same as theta B, at least in this situation. Okay. So the change in slope between the tangent of A and B is the same as the angle the point B makes with the horizontal. Okay. So all of this is just to explain the elastic curve. Okay, you don't need to go through, I mean, this extra information here just to explain the concept. Okay. What is important is drawing the elastic curve right here. Okay. So once we draw the elastic curve, the next thing to do is to draw your bending moment diagram. Okay. So for a cantilever, the bending moment diagram is a negative moment. So this is my bending moment diagram. Again, I'm assuming we know how to do these things already. So this is PL for the bending moment. So this is negative. Okay. This is PL for the bending moment diagram. Okay. But then when we go back to the slope equations, it says the M over EI. Okay. So the M is the bending moment. So we need to divide the bending moment by EI. All right. We don't know what EI is now. I've not given you guys any information about EI. So I'm just dividing M by EI. So this becomes PL over EI. Okay. So this is your M over EI diagram. Okay. You hear this term a lot, okay, being used throughout the semester. M over EI, M over EI. It just simply means that dividing the moment by the flexural rigidity. Okay. So once we have that, the next step is to take note that finding slope between 2 points is the same as finding the area of the moment over EI diagram between those 2 points. All right, so the geometric approach, so this is where geometry comes in. We are finding area. Okay, so I can go back here and write that this is the same as finding area of the M over EI diagram, okay, between points A and B. So here, so this is my point A, this is my point B. So it means that I have to find the area of this triangle. Okay. So the area of this triangle will be what? So the area of triangle is half base times height, right? That's how we know how to find triangles, half base times height. So generally, area of triangle is equal to half base times height. So here, my base is L. My base is L, and my height is PL over EI. Okay. So it means that I'll end up with 1 over 2 half base. So the base is L, then the height is PL over EI. Okay, so this is your equation. And then let's take note, this is a negative height, so it's minus PL over EI. All right, so let's take note of that. And when you solve it, this will give you PL squared over EI, or minus PL squared over EI. So this answer here, which is minus squared PL, minus PL squared over EI, will be the slope between B and A. Okay. So once you find the slope between B and A, typically the questions will not be stated that find slope between 2 points. The questions will be in such a way that find the slope of a line or of a point, which means that we want to find a slope with respect to the horizontal, or find the angle theta with respect to the horizontal. Okay. So this involves a bit of geometry most of the time. Okay. So once we have minus PL squared over EI, it means that I can do a bit of comparison, right? Which I have already done from this computation, that because this is tangent A, different color. This is tangent A, or tangent from point A, and this is the horizontal line. And this is the tangent from B. So this is point B somewhere here on the elastic curve. Oops. Let me put, so here it has 2. Thank you. This is 2. Okay. 2 EI. Please take a note of it. Thanks for the correction. Okay. So here we have already established that in this case, right, it is not always. In this particular case, my theta BA is the same as theta B. Okay, so in this case, so it makes things easier for me, which means that whatever I found for theta BA, like I said, I'm using corresponding angles or trigonometry or whatever. Theta B is the same as theta BA, and that is minus PL squared over 2EI. Okay. So just a few things to take notes. If the M over EI diagram is positive, then it means that your angle, the angle that we're trying to measure, the angle is measured counterclockwise. Okay, so take note. And then if the M over EI diagram is negative, then the angle is measured clockwise. I mean, these are sign conventions we go with. Okay, they're just sign conventions. So in our case, for example, where we have a negative in front of, let me exaggerate the negative. All right. Once we have negative, that it means that the angle is measured what clockwise. Okay, so going back into the space, I can put in the arrow to indicate that these angles are measured clockwise from tangent A towards tangent B. So there's just the directions of the angles, okay? And the angles are in radians, not degrees. Okay, they're in radians. But again, just be careful when you're using your calculator. Your calculator can be in degrees and just do your normal calculations. But whatever answer you get is in radians. So they're usually in points, very small. Okay. Um, okay. So I'm saying that the angle here, theta, is in radians. Okay. And if your M over AI diagram, so that's if your bending moment diagram is positive, it means that the angle is measured counterclockwise against the clock. But if your moment diagram is negative, then your angle is measured clockwise. Okay. So with this example, our moment was negative. All right. We had a negative bending moment, which means that our angles will be measured clockwise. Okay. So that's like in basic terms what goes into the bending moment diagrams. I mean, in terms of trying to find slopes between points. Okay. So I think the other thing was that we should find, so here theta b is equal to theta ba. This show how you measure. How do I measure what exactly? Uh, you cannot unmute and ask the question so that maybe I can understand what you want to say. How do I measure the angle? Difficult to understand because to measure the angle, um, I'll know P, I'll know L. So in this case, for example, here I'm using variables, right? I'm using variables to find my theta. But then in typical examples, I'll know the value of P, I'll know the value of L. I also know E, I also know I. So once I put into this equation, I'll get like an actual value, maybe let's say 0.00, maybe 2, and this is written in radians. Okay, so either the whole radians or just the short form rad. Okay, so that your theta, let's say maybe theta b will be equal to minus 0.002 rad. Okay, so that's how we find the angle using the equation. I hope that helps.
She would prefer if you could repeat what you said. It seems you are glitching up a bit.
I have a feeling that we have too many people connected to it. I don't know. Maybe it's just something I'm thinking. Maybe that could be a reason why you guys are having that glitch. Because my internet seems fine from here. So maybe I don't know.
I don't think so. Maybe it could also be the internet connection.
Sorry, come again.
Maybe it could also be the internet connection over here.
Oh, okay. I'm hoping it's just a today issue and it shouldn't continue. Okay. So I'm saying that yeah, I know students don't usually like anytime you try to use variables to explain a concept, right? Because like what's all this plenty letters and plenty all of that. But that's the best way to understand what's going on. Okay. So I'm saying that normally, right, you would know what your P is, you know what the load P is, you know the length of your beam, you'd also know the E, which is a Young's modulus, and you'd also know your I, your moment of inertia, right, which will be given. So if you have these parameters, you only have to replace them or put them into this equation, the minus PL squared over 2EI equation, and then you find a value. Okay. So the value it can be, in this case, maybe it can be minus, oops, instead of that I'm doing, it can be minus 0.002. All right. And whatever answer you find is in radians. All right. And you need to leave your answer in radians as it is. You don't need to convert to degrees. Okay. So once it's in radians, it's fine. Okay. So let's solve maybe an example that has actual values. Do I have one here? Okay, so before I do that, let's look at a second theorem. Okay. Then we can come back and then solve more. I jumped this one. I jumped okay, I jumped finding theta c. Okay. I jumped that one, but it's the same concept. Theta c, in this case, because of the fact that the tangent at A is horizontal, it means that theta c would also have will be the same as theta CA. And theta CA is the area of the bending moment diagram between C and A. So let me just write this over here, theta CA. If this is a bending moment diagram, let me just make a copy of it. Okay. If this is a bending moment diagram, and this point is C, your C is somewhere here, right? So it means that you need to find this area. So your theta CA is simply the area that I've shaded between A and C. Okay. So C is at the midpoint, which means that this height over here will be PL over 2EI, right? Using similar triangles. Okay. So this is what is a trapezium. Is it trapezium? Yeah, trapezium. Right. And for a trapezium, the area of a trapezium. Let me exaggerate it a little with a different color. Okay. So here's A, this is B, and this is H. And the area is what? Half into bracket A plus B times H. So that's the area. You cannot do that. I'm saying that whatever answer you find is in radians. All right. When you put in the value of P, the value of L, the value of E, and the value of I into the equation as you've been given, that answer is already in radians. So you cannot find your answer in degrees because whatever answer you get after the computation is already in radians. Okay. So once if you convert your answer to radians, then means that you are converting from radians to something else. All right. And that will not be in radians. It might be some other value which would not be correct. Okay, so your answer is already in radians. So here, so this is the area of a trapezium. All right, just in case we had forgotten, trapezium or zoid or whichever one we are looking at. Trapezium. Okay. So here it means that theta CA is equal to half sorry, excuse me. So half of PL over EI plus PL over 2EI And then the length here is L over 2. Oops. L over 2, so times L over 2. And again, all of this is already negative because of the fact that um, the moment is negative, okay? So if you do that, you should end up with minus 3 over 8 PL squared over EI. Okay. If you do this computation. Okay. The other approach would be that you take this diagram as it is. Okay. Then instead of using the trapezium equation to find it, one simple method will be to divide it into triangles and rectangles. Okay. So you have here 1, you have here 2. So this is area 1 and area 2. So for area 1, again, it's the same CA. For area 1, it's simply PL over 2EI. So this is L over 2. The area of a rectangle is length times base. Okay. So times L over 2. So that will be for the area 1. Okay. Again, let me just bring the negative in front. And plus, so now we have this area to deal with. Okay. So let's find this height. This height is simply here is simply PL over EI, which is the entire height here. So the entire height is PL over EI minus the height of the one at C, which is PL over 2EI. So this should give us a PL over 2EI anyways, so it's fine. So for the triangle, it's half base, where the base is L over 2 times PL over 2EI. Okay, so if you do it this way, you'll still end up with minus 3 PL squared over 8EI. Okay. So again here, if you know what P, if you know what L is, and you know what E and I are, you can input them into the equation, and then that will give you your theta CA. Okay. Again, theta CA is the same as theta C in this case. Okay, it's not always the case. Please take note of that. Now let's look at the second theorem, theorem 2. So please take note of the theorems. Okay, let's take 5 minutes break. Let's stretch our legs and then we'll come back and continue. Okay. So let's take some break. Let me just pause and then we can take a break. So now let's look at the second theorem, which is the one that helps us to find the deflection. So it states that the vertical deviation, I'll explain the concept very soon. The vertical deviation of the tangent at a point B on the elastic curve with respect to the tangent extended from another point equals the moment of the area of the M over EI diagram between the 2 points. It's a mouthful, but it's not anything crazy. Let me just go up a bit and then copy something. Yeah, so let me just go back and copy this guy here. Let me get as much as I can from this diagram. Excuse me. Okay, so we have this. Okay. So this initial position, all of the information from previously are the same over here. Okay. So let's look at what the theory means. Um, so the vertical deviation of the tangent at point B. So this is our point B, okay? Let me not so let me just underline the tangent at point B on the elastic curve. Okay, we already know what the elastic curve is, right? So the curve is a little sea blue color. Okay, so the tangent at point B. So this is point B. Let me use the highlighter. So this is point B on the elastic curve. Yellow is a bad highlighter. Okay, so this is a point B on the elastic curve. Okay, so that deviation, okay, which is coming from a tangent extended from another point. So we have this tangent here, tangent A, right? So this is tangent A, which is extended from point A. That's vertical deviation, which then becomes this distance over here. Okay. So extending point B to the tangent from another point. So that here is what you call the vertical deviation, right? So um, the vertical deviation can be written as T. So in this case, TBA, because we are using the point TBA, or some books will go with delta BA. It's the same idea. So to find this vertical deviation TBA, okay, here I don't need to find, let me just take away the angle so that it's my thing looks less okay. I think this is yeah, clean up. Okay. The 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 deflection of B is here. So this is your delta B. Okay, and this is your delta A. Okay. Deflection is simply the vertical difference between the initial position and then the current position. All right. So once there's that deflection, we have the elastic curve forming, and delta B or delta A becomes those two deflections. Okay. So the moment area method doesn't straight away find these deflections as compared to the with the double integration method, that once you are done with your integration, whatever answer you find will be the deflection of that particular point. But with the moment area method, it's taking into consideration 2 points always. All right. So it's saying that with rotations or with slopes, you find the change in slope between 2 points. In the same way, with deflections, you first have to find what you call the vertical deviation. All right. So you first have to locate a tangent or a point on the elastic curve, which is of interest to us. So in this case, point B. So point B is of interest to us on the elastic curve, and we want to find should I say, the difference or the vertical difference between point B on the elastic curve and then the tangent extended from A. Okay. So the tangent extended from A, which is what I've done the highlight to, it meets B at this point. Uh, Let me use this color. It meets B at this point. Okay, so this is the point it meets B at. I mean the vertical deviation. So this height here becomes the second theorem. Okay, or from the theorem we are saying that this vertical deviation TBA, it is equal to the moment of the M over EI diagram. Okay, where we understand moment to be what? Force times distance. All right. Um, we have different kinds of moments based on what the the main entity is, right? So we have what you call, let me just put an aside over here. So we have the force moment, which we all know to be equal to the force times the perpendicular distance. Okay. We can also have area moments, which is basically what this is all about. Okay. So that is equal to the area times its perpendicular distance. Okay. We have other forms of moments, right? The key thing is that moment is always an entity times its perpendicular distance. All right. So if that entity is force, then it becomes force times perpendicular distance, and that becomes the force moment as we know it to be. And if the entity is area, in this case, which is what we are trying to look at, then it becomes area moments, or as the name implies, moment area approach. Okay. So what it means is if I draw my bending moment diagram, so let's say I have the arbitrary shape. So I draw my bending moment diagram. So this is a moment between A and B. So this is your bending moment. So let's say the M over EI diagram between A and B. Okay. So now let's assume let's assume that this point here is the centroid, right? Or the center. So this is the centroid of this shape. So what we mean by moment, it means that if I want to find TBA, which is the vertical deviation between B and A with respect to B, then I need to find the area of the M over EI diagram. So find this entire area with a green shade, then multiply it by the perpendicular distance, okay, which we know that to be, this is defined as what? The distance from the centroid of the shape to the point of interest. All right. So here, because we are looking at the vertical deviation under B, B becomes our point of interest. Okay. So we need to find the moment about B. Okay. So we need to know this distance here. So let me call it X bar. All right. So from the centroid to B becomes X bar, which means that TBA or TB slash A, because the area of the M over AI diagram, again, between A and B times X bar. In the same way that we can, the same way that we can formulate an equation for, or solve for the vertical deviation at B with respect to a tangent coming from A, we can also find the vertical deviation at A, okay, when we have a tangent extended from B. Okay. So this height here, this entire height here becomes your vertical deviation at point A on the elastic curve when you extend a tangent from B. Okay. So again, the same same idea. TAB will again be equal to the area of the M over EI diagram, which is between A and B, times the perpendicular distance. But this time around, you are looking at distance with respect to A. Okay, so it means that we have to find this distance here. Let me call it x dot. Okay, so it means that times x dot. Okay, and this is the difference between the two. Okay, so where we want to find the vertical deviation determines where we want to take the moment about. Okay, so the general equation for these vertical deviation, I put it that over here, TBA would then be equal to x bar m over AI dx, where the limits are from A to B. So this is a general equation for the vertical deviation. Okay. The entire theorem can just be written as a mathematical equation. Okay. So take a note of that right here. Okay. And with this, we take moment about B. So let's say generally, let's say we have maybe TQR. Yeah, I'm just going to explain the Q is the first subscript. Let me just type first. First subscript. And this denotes the point where, oops, where the deviation is determined. Okay, so just so that we know. And also, um, and about which the moment is evaluated. Okay, and then the second subscript. This denotes um, the point where the tangent to the elastic curve is drawn. Okay, and just to explain the two, what's the name? The two subscripts for us. Okay, so the most important here is understanding what the deviation is, and also where to find your moment. Okay. So let's look at our previous example. I'll just bring that one up. The same example. Where are you? I have this example. Let me copy everything. Okay. Hopefully copies. Okay. So I don't think I need don't need this. I don't need that. Let me take this one off. Okay, the one again. All right. I think I can take this one off too. All right. Oops. Too much deleting. Oops. Then everything comes back. Okay. All right. So what I have interest in, so this is point B, right? So here's point B on the elastic curve. Okay. And this is the tangent from A. So it means that this distance here will be my vertical deviation of um, point B with respect to the tangent being drawn from A. Okay. So I need to find TBA. Okay. Again, in some cases, your vertical deviation might be the same as um, the actual deflection of that particular point sometimes. In this case, it's the same. For example, if I'm to draw the beam again and then draw the elastic curve, here is my delta B. Okay. So if there's an initial position of, so B was initially at this point and now B is here. So let me say maybe B naught and B1. Okay. So the delta B, which is the deflection at B, is just the difference between the initial position of B and then the current position of B. Okay. In this case, it coincides with the vertical deviation, TBA. And the reason is because the tangent at A is horizontal. Okay. If the tangent at A was a different uh, um, 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 direction or orientation, um, then TBA would not be equal to delta B. Okay. But in this case, that is what we have. Okay, because of the fact that uh, tangent A is horizontal. Okay. So again, the first thing to do is to draw the bending moment diagram. Okay. So you take your structure and then draw the bending moment diagram, which again will be this shape right here. Okay. So this is again minus PL over EI. So that you are drawing the M over EI diagram. Okay. So now to find TBA is the moment of the area, right? So what do? We find the area first. So the area will be minus PL. Let me do it this way. Let me make it bigger so we can all see. So PL over 2EI times L. So this becomes the area, half base times height. Okay. Now the next thing is to find the center of gravity of this rectangle, sorry, of this triangle, and then find that distance. So this distance here will be the X bar. Okay. So this is geometry. Okay. X bar will be equal to 2/3 of L. Okay. If you have a triangle, um, let's say in this shape, okay, your center of gravity or your center to pass through this line. Okay. So that if this whole thing is L or whatever value it might be, the distance here, let me call it x1, and the distance over here, x2. So x1 will be equal to L over 3, and x2 will be equal to 2/3 of L. Okay, so these are to find the centroid or the center of gravity, okay, of a shape. So here we can see that our x bar that we are looking for, it corresponds to x2. Okay. So that it means that times 2/3 of L. Okay, so this is x bar, and this is the area of M over EI. Okay, times x bar. So once we have that, that means that TBA will be equal to what should I give you? So that'll give us minus PLQ over 3EI. We have already established that in this case our TBA is the same as delta B. Okay, so that the deflection at B is the same as the vertical deviation between point B and then the tangent extended from A. Okay. So if you go back to your notes from last week, you'll see that we ended up with something very similar. Let me pull it up. Where is this? Last lecture 2 last week. Where would you be? Oh, I didn't solve that. Oh, I didn't. Okay, I thought I solved a question on there. Say, what's the name? Cantilever beams. That was last week. Okay, that's fine. So these are basically how we go about these types of questions. So we can expand it. We can expand all of these to other areas. All right. So I think in your so if you go to V Campus, you have some notes and then some examples to look at. I think one of the examples, if I remember correctly, so let me call this um, example three, maybe 3.1. So this is lecture 3. I think it's the same as example 8.5 in the Hibla. Okay. I know there's some, okay, 2B somewhere and then 1L somewhere. Okay, so what the Hibla, I think it has this structure. This is 10 kilonewtons, A, B, and C. Okay. And it says we should find, so this is 5 meters each. 5 meters each. And then we're given a value of E. E is equal to 200 GPa. And I is 360 times 10 exponent 6 mm 4. Okay. And the question says we should what's the name? Determine the slopes. All right. So let's start with determining the slope. So let's say question 1. Determine the slopes theta C and theta B. So take note of it. It did not say find theta B A or theta B or maybe CA. Normally, you are not asked to find these things. All right. But the theorem make use of theta C and theta BA. So again, we have to apply geometry to translate that information into finding R theta C and R theta B. So let's look at the solution steps. Okay. So these are the solution steps. So the first thing to do is that we can draw and then label the elastic curve. So that's the first thing. Draw and label the elastic curve. And also draw our M over EI diagram. All right. Then define any trigonometry, shapes and all of that. Yeah, from there we can solve for the questions. Okay. So it's just what we did earlier. Let me just take this one off. Okay. We want to find, so here we want to find theta. What's the name? Yeah. So we want to find theta BA. And also we want to find theta CA because that's what the theorems require us to find. Without that, we cannot find anything, right? So you cannot straight away go and find theta B and theta C. You have to follow what the theorem states, which is to find the change in slope between 2 points. They use geometry or trigonometry to find the actual slope of the points on the elastic curve with respect to the horizontal axis. Okay. So again, with this example, it makes things easier. So theta C, theta B are the same as theta CA and theta BA respectively. Okay. So let's go through that. So once we're done with the elastic curve indicating all the angles that we need, our next point is to draw the bending moment diagram. Okay. So our bending moment diagram. Maybe I should increase the size of this a little bit so that it's work. Okay. So our bending moment diagram. Um, so bending moment with a cantilever straightforward. So this is our bending moment diagram. Okay. Again, what's the name? So this is 100 over EI. If for some reason you don't know how to draw those things, kindly let me know. I'm assuming we should know that from our basic structures class. You can type in the chat and then I can maybe be alerted, right? But it's P times L. Okay. P is 10, L is 10, so that's 100. Okay. So here we have A, this is B, and this is C. Okay. So at this point, then somewhere here too, we have 50 over EI. So these are the points on the bending moment diagram. Delta CA. Okay, that's fine. So let me delete this and then maybe get you a proper curve. Okay. Let me just delete this. Delete. Let me see if I can draw a proper curve so that it doesn't become confusing. Delete. And then this last bit also delete. Let me just copy from what I had previously. Where were you? Okay, I think maybe this one might help. I have to make a few more changes to this. Okay, so let me use this one. Let me take this guy away. So here, there's a few things to note. So now this is my B, and this is my C. Okay, it doesn't change much. So this angle here is theta CA. And then, so maybe that's B. So this is my B. I can draw another tangent. So this is theta C. Okay. And this is tangent C, just so that everything works. So the theta C, theta CA, just trying to change parameters. It doesn't change anything. Okay. So I can draw another tangent at this point. So it's going to be an interesting one to draw. So let me use let me exaggerate it a little. Okay, let me use this color. Would that even work? That's a bad color to use. Let me look for a different color and see if I can maybe use the ash. Yeah, it's faint, but it's fine. So this is tangent B, super faint. So this is tangent B. Okay, so then the angle it makes with tangent A is theta BA. Okay, so I think this should maybe help us to make things look easier. I mean, less confusing than the previous one. Okay. All right. So once we draw a bending moment diagram to find theta CA is simply the area of the triangle, right? So this is negative, so minus, what's the name? Minus half of base times height. So the base is L, where L is what? 10. So the base is 10 meters, and the height is 100 over EI. Okay, so this should give us minus 500 over EI if you do the math. Okay. Now we know E. Okay, E to be A is again. So this is where the units thing comes into play. I think last semester when we were looking at I think was it engineering materials, we spent a bit of time to go through all of these units and all of that, so that you multiply like the same units, so that you end up with the correct answer. Okay. So let's take a note of a few things. This is in meters. This is in kilonewton meter over EI. Okay, so the 100 is kilonewton meter, the 10 is meters, which is the length. Okay, so it means that your equations are already being analyzed in meters and kilonewtons. Okay, which means that your EI, which I have over here, should also be formulated in that manner. Okay, to make things easier for us. So GPA, I can convert 200 GPA into 200 GPA is the same as what? 200 times 10 exponent 9 newtons per meter squared, sorry, not millimeter, meter. And this is the same as 200 times 10 exponent 6 kilonewton per meter squared. 360 times 10 exponent 6 mm4. I need to convert it into what? Meter exponent 4. So it becomes 360 times 10 exponent 6 times 10 exponent minus 12 meter 4. So this will give me 360 times 10 exponent minus 6 meter 4. Right, we've gone through some of these examples already on how to do these conversions. Okay. So it means that my E would be when I'm drawing the tangents, when I'm drawing for the tangent, should it also pass through the point B? So each so basically each point of interest to you would have its own tangent. Okay. So for this question, we are looking at theta B and theta C. All right. So because we are looking at theta B and theta C, we need to draw tangent at those points, or tangent passing through the points B and C on the elastic curve. Okay. So that's how come I did that. All right. For the fixed point is point A. All right. So let's look at it this way. There are 3 points, A, B, and C, and each point is of interest to us. So for all these 3 points, we are drawing their tangents. Okay. It so happens that point A does not undergo any rotation, right? Or even deflection, because point A is a fixed point. So because of that, the tangent at A will always be a horizontal line. Okay. So for fixed supports, their tangents are always horizontal. Okay. For a roller support, the tangent will not be horizontal. Right. It might have some slanting. Okay. And for other points on the structure, they are likely not to be also horizontal. There are a few instances where other points on the beam would end up being horizontal. We'll see one of those examples, but normally they are not horizontal. Okay. So I think that's what I can say to that effect. Okay. So our E here is 200 times 10 exponent 6. Then our I is 360 times 10 exponent minus 6. Okay. So these are the information that we need from these calculations. So here you can do the math, then you end up with minus 0 0.0, I think 0.694, and whatever answer you get is in radians already. Okay. And usually we don't like to write answers in this form, all right, because it's not engineering enough. Okay. So the best way is to convert this into, I think, a significant figure. Is that what? Yeah, that's what we do. So it becomes minus. You take the zeros too. So you take 1, 2, 3 to the 6.94. So it becomes 6.94 times 10 exponent minus 3 radians. So this is the engineering way of writing your answer. Okay. So the negative here, the negative that we see here denotes that the angle is measured or the slope, whichever we want to look at. So angular slope is measured clockwise. So the angular slope is measured clockwise. Okay, so that's something to take note of. And again, here, as I mentioned, in this case, your theta C is the same as theta C. So whatever answer you get is the same as theta C. You can apply the same idea to find theta B, which is the same as theta BA. All right. So that will be the area of this portion. So you can try that on your own. And then you find theta, what's the name? Theta B. I think the answer would be minus 5.21 times 10 exponent minus 3 radians. So this is the answer. Right. There must be a negative sign in front of the half. All right, so and then put it there. So there's a negative sign over here. Let me -1/2. Okay, all right. So this is basically this is what goes into the calculations. Okay. So let's say we want to solve, maybe find the deflection at B. So let me use this same example. So this is question one, find delta C, delta B. And the question two will be find delta C. Okay. We know delta C in this case to be the same as TBA. Okay, it's only under this scenario. Please take a look. Okay, so again, similar idea. Delta C is equal to the M over AI diagram, or the M over AI diagram times the perpendicular distance. So that is the same as the moment of the M over AI diagram. So let's find the area. So the area is pretty much the same as what we had earlier. So it's minus half times 10 times 100 over EI. Then the distance will be from the centroid towards C, because you are finding, oh, sorry, not TBA, TCA. So you are finding TCA. Okay. So that will be 2/3 of L. Okay, so 2 over 3, and L is what, 10 meters? So 2 over 3 times 10. Okay. So then this will give us, if we do the math, I think I have the answer here. This will give us a lot of values. 10,000 over 3 EI. So negative 10,000 over 3 EI. We know what E and I are already, so this should be equal to minus 10,000 divided by 3 times 200 times 10 exponent 6. Then let me increase that. So 360 times 10 exponent minus 6. Okay, so that should be equal to so that'll give us I think minus 0.04 maybe 46. Yeah, minus 0.046, and this is in meters. Okay, because everything we're dealing with was in meters, so this is in meters. You can convert it from meters to millimeters. Yeah, so when your conversions are wrong, your answers will automatically be wrong. So the conversions are very important. The units are critical. Otherwise, you would end up with the wrong answer easily. Okay. So this is in meters. We can convert that to millimeters. And this should give us minus 46 in those 3. So minus 46.3 millimeters. Okay. Again, the negative here indicates that it's a downward deflection. Okay. If it's an upward deflection, it will be a positive value. Okay, because then you have a positive moment. Okay. So I think this is just something general with respect to how the moment area method works. Okay. Now let's look at a more interesting example. Should I jump this example? Because of time constraint. Okay. Okay, let me just look at this. I'll call it, I'm jumping the second example. I'll upload examples to the V campus. I think they are already uploaded also. So it should be a fairly easy thing to look at. Let me see what I can drag and bring. So let's look at this example again. This is example 8.8 from your, what's the name? From the Hibla. So you can always check that up. So here, maybe it's a little bit more, it's a little bit more complex, but isn't that much complex too. Um, Theta B is equal to theta B over A. It has to do with the fact that it has to do with the tangents. All right. Going back. So let me use this example. Going back to the tangent, right? So this is tangent A. So here is tangent A, and this is tangent C. So the one with the oops, the one with the scalar. So this is tangent C. Okay. Now tangent A happens to be horizontal. Okay. So the reason why theta B, or maybe let's say theta C is the same as theta C over A is because of the position of tangent A. Right? So tangent A is horizontal, which coincides with the horizontal line, right? So the change in slope between tangent A and tangent C will be theta C over A, all right? But then, because tangent A is horizontal, it is the same as finding theta C, right? So using the idea of corresponding angles. So that's how come in this case, theta B is equal to theta B over A, or theta C is equal to theta C over A. The second example would expand our understanding a little bit more. Okay. Um, all right, so let's say we have this example. All right, so it's a beam of a length of so the length of the beam is how many meters? 8 meters. The total length here is 8 meters. Okay. And we have a load of 40 kilonewtons at 2 meters from B. All right. Then we have this point of interest to us. Let's call that point C. So maybe where the load is, we can call that point D. Okay. And we are to find the slope at C. So find slope at C. Okay. So that's find theta C. That's what we are supposed to find, not theta CA, not theta CD, not theta CB. Find theta C. Okay. Now, um, let me make things a bit cleaner over here. Why always slope at C? They're just variables. It could be slope at K, it could be slope at M, it could be slope at Z. I'm just using variables. All right. So instead of slope at C, I can call this point maybe point K, and I go like find slope at K. Okay. So find theta K. It doesn't do anything. It's just variables. Okay. All right. I'm just going with this because of what it's in the textbook, so that we all have the same thing when we are going through it. Okay. So let me just go back to the C. And normally you would find out that usually when we are labeling points on the beam, the supports are usually A and B, and then other points are maybe C, D's, or E's, or whatever. Okay. So let me do a bit of cleaning over here. Let me just clean the whole thing and then take you through it properly. Let me bring up my ruler. Okay, so let's start with the beam. Go up a little bit. So this is a beam. Okay. Okay, let me draw my curve. Hopefully it looks nice. My curve is a bit funny. It's actually looks more like this and that. Okay, so this is the curve. So here, so this point is point C. So here we have our point C. Okay, so let me draw. So this is A, this is B. Okay, so let me draw a tangent from A. Let me, okay, let me see what I can do. Let me just move C a little bit away from this point. Okay, let me put C somewhere here so that at least I can get the curve the way I want it to look like. So I can draw this tangent which is passing through C. Okay, then I have another tangent passing through A. Let me just passing through A. Okay. So passing through A, let me use a green color for that. Okay. So let me just label them nicely. This is tangent passing through C. This is tangent passing through A. Okay, it's just naming. Okay. Now, I think these 2 points should help us. I should have extended this a little bit. Let me just extend this line a little bit. Let me see. If you want to draw something you want to redraw, that's always a challenge. Okay. So this is fine. Okay, so we have all of that. Okay. So the intersection between so this is the intersection between tangent C and tangent A. So that intersection, which is this angle right here. So this angle will be theta CA. So it's the angle between the tangent C and A. Okay. Now, if you look at joint C or point C, sorry, I can draw a straight line or a horizontal line at where C is on the elastic curve. So go up a little. So I have something like this. Okay. So that the angle it makes with the horizontal, this angle here is theta C. And that's what we've been asked to find. Okay. The angle point A makes with the horizontal, this angle here is theta A. Okay. Now, so if this is the initial position, I'm making it bigger so that we can see. If this is the initial position of C, and now C has deflected, it means that this distance here becomes delta C, which is a deflection at C. All right. There are a few things that I'm putting in here just to explain the concept to us. Now, this is point B. Okay, so here's point B. And then we know that per the second theorem, the vertical deviation from a point on the elastic curve to any tangent can give us that vertical deviation, right? So let's say, let me do this. Let me use a stroke to delete a portion of this for now. I don't need to have this whole thing show. So that I can, so let me put here tangent, where's the color? Tangent um this is C, sorry. Okay. So it means that if I'm able to define the vertical deviation, so this means that if I should extrapolate point B, this is where it's going to land on the tangent at A. So this angle or this distance here is my TB. Okay. Now, if you take a second look at what I've done, if you take a second look at what I've done, you could actually see a triangle being drawn. Okay. So A to B is a horizontal. Can we take the point of interest at B? We could have landed on C. Yes, you can also extend it. Again, this becomes a geometry problem, right? At this point, it's more of a geometry problem than anything else. Assuming that I extended, so I'll answer both questions. Assuming that I extended this, okay. So it means that the vertical deviation from B with respect to C would be this, all right? Oh, sorry, to be somewhere here, not all the way to the end, so to be somewhere here. And that would be what? T, B, C. All right. So you can also have that. Okay, so there are so many options available to you in solving this particular problem. I'm going with the easiest of them. Okay. Or you can have all of these computations in there to make life easy for you. Okay, so just take a note of it. Okay. So here I was saying that if you look at the beam AB, then you look at the tangent A, then you look at the vertical deviation TBA, you can pretty much put together a triangle. Okay. So if you come to the right, I have this triangle right here. So there's the length AB. Then I have here the vertical deviation TBA. And then I have, let me just change the color. So this is tangent A. Okay. Then let me take this one away. I don't need that over here. Okay. All right. Well, it's what makes mine the easiest. It's my understanding of the concept. All right. Um, our understanding changes a little bit depending on our perspective. And then again, with these types of questions, there are different ways to solve the problem. All right. Mhm. So let me make this, so I'm saying phi. Let me make this one theta A. Okay. So we think the goal is to find theta C. So that is the plan. What am I looking for? To make sure that I have not missed anything. Okay, I'll explain the concepts again. All right, so the goal is to find, let's first find theta A. Theta A is going to help us to find theta C. Okay, so to find theta A, we can simply use angles, and then the Pythagoras theorem to find theta A. Okay, so let me just delete this over here for now. I'll come back to it. Okay. why are we finding theta A? So this is the idea behind this approach. Okay. So I have the beam and I have this angle here. So this is tangent A. And I also have somewhere here tangent, it looks too straight. So I have here tangent C. Okay. So I have this here. I know this angle, theta A. Okay. Um, somewhere here, I know this angle too, which is theta C. All right. I also know this angle here to be theta C A. Okay. So clearly we can see that theta A is the same as what theta C plus theta C A. Okay. Again, so let me do it this way. Let me draw. Let me just again use the same colors to show you. Oops. Go down a little bit. Okay, great. Okay, so we have here to be theta A. That much we know. And then so let me put this over here. Okay. So I have a line slanting slightly down. Okay, this looks too horizontal. This is great. Okay. So I have this line slanting down. Then I have a horizontal here. Okay. What this means is that oops. So again, whatever angle I have over here, so let me call this angle phi. Whatever angle I have over here, phi is the same as theta A, corresponding angles. All right. But then a portion of phi, so a portion of phi over here is theta C. Another portion of phi here is theta CA. All right. So it means that if I find theta A and I find theta CA, then that should help me to find theta C, which is obviously the final answer that I'm looking for. Okay, so here becomes geometry kind of problem, right? So sometimes the challenge with the moment area method, it's your understanding of geometry. Okay, and one of the better ways to understand geometry is to what's the name? Is to solve more questions. Okay. I would end the class here, have a meeting in the next 5 minutes. I've forgotten about it totally. So I'll end the class here and then we'll continue again next week. But what I'll do is that I'll complete this solution before posting on the V campus. When we meet again next week, I would what's the name? I'll go through that bit as well, and then at least for us to understand. Okay, I have to run. Sorry, I just remembered. Um, and let me see if I have a bit more time. Okay, I think I have some 5 minutes. So let me use that to solve that quickly, and then we can go. All right. So again, let me just take all of these things off so that at least you see what I'm writing. Hopefully, once someone should promise me in the next 4 minutes or 5 minutes. That's my time is up. Okay. So quickly, let me just do this. So going back here, I need to find theta A. All right, so to find theta A, you first need to find TBA. Can I finish this in 4 minutes? I doubt. Okay. So theta A is equal to theta C plus theta CA. So mean that theta C is equal to theta A minus theta CA. Okay. And to find theta A, we come back to this diagram over here. It's the same thing. The theta CA is over here. So this angle here, this angle, oops, sorry. This angle here is theta CA. Theta CA is the angle between, I don't think I'll be able to finish. So let me just explain to you. It's between tangents. So this is tangent what's C and tangent A. So that's theta C. So that's the difference in the tangent. All right. But then the angle the tangent C makes with the horizontal is theta C. So if I have this tangent over here, no matter where I draw the horizontal, right? No matter where I draw the horizontal, the angle it makes is always the same, right? Do we agree to that? Okay. So yes, in this case, I have my angle, my horizontal a bit skewed, some distance away, but I can push it all the way to here. And once I push it to this point is the same theta C. All right. So that it means that the total angle here, or the angle on this point from the horizontal to the tangent at A becomes this angle theta. Let me call it phi, where phi is equal to theta C and then theta C. Okay. Yeah, so we'll continue with it next week. Okay. You can play around with it. The key thing is to find the main thing is to find in theta A, and you can use angles to find theta A. All right. So here, tan theta A is equal to TBA over L, right? Angles. Okay. But because the angles are very small, we can assume that tan theta A is almost the same as theta A. All right. So then it becomes theta A is equal to TBA over L. Okay. So this equation then becomes theta C is equal to TBA over L minus theta CA. Okay. So the goal is to rewrite the equations in terms of the theorems. Okay. So once they are written in terms of the theorems, then they become easy to solve. Okay. So from here onwards, we draw a bending moment diagram. Okay. Then we find TBA, then find theta CA. Put them into this equation and then find theta C. Okay. All right. So I've got to run. We'll talk again next week or meet again next week. Okay. Hopefully with that one, we can move forward a little bit more. All right. Thank you and enjoy the rest of your weekend.